So this is John work with Professor Hyun Kwang Kim from POSTECH, and in this work we just use very simple argument, that is counting, and using this method we prove many well-known results on the upper bound of codes. And we generalize this method, and we obtain some new upper bound on size of codes. So in the introduction, I just introduce the codes and some problem, and what we'll do in this talk. And in the second section, I use a counting method to prove well-known bound like Johnson bound, Plotkin bound, and Delsarte linear programming bound. And we generalize this to get some new upper bound on constant weight codes. And in the section 2, we only deal with the binary case. But all of this can be generalized to the q-ary case. q-ary codes. So first, let me give the definition of a code over. Well, we just start with the binary case. So F just is 0 and 1, and a binary code is just a subset. So this is just a subset, not necessarily linear, so we study nonlinear codes. And an element of a code is called a code word. And this is the minimum, the distance between two code words is the number of coordinates where they differ. And the minimum distance is the minimum distance between any two different code words. So one of the fundamental problems in coding theory is to find the value of AND and ANDW, where AND is the maximum number of the code word in any code of length n and minimum distance at least d. And ANDW is the same thing, but we require that the code word should have a constant weight W. But it turns out that to determine the value, exact value of this function is not easy problem. So people try to get a lower bound and an upper bound of this function. And in this talk, we just talk about the upper bound. So in this talk, we consider C as a matrix. We write C as a matrix where each row is a code word. So if the code have m code word, we have a matrix with m rows, and the number of columns is n. So what we do is we will count the number of submatrices of this matrix. That's the general idea. So let me start with the most simple, the simplest case is counting the 1 by 1 submatrix. That's it, count the number of entries which satisfy some property. So here let's start by counting the number of ones or zero of this matrix. So this gives the well-known Johnson bound. This was proved in 1962. So this bound, it looks simple, but in many cases this gives the very good bound, even exact value for ANDW. So but the proof is very simple. We consider C as a matrix, as I say, have m rows and column, And let's try to count the number of ones of this matrix. So if we look at the rows, because this is a constant weight code, each row has weight W. So for each row we have W1. So we have totally M rows, so that the number of 1 is MW, right? But if we look at the column, so let Xi be the number of ones on the I column. So for each I, we collect all of rows that have 1 on the I coordinate. And we collect all of that rows, and we delete the I coordinate. And we will get a constant weight code of length n minus 1. And the minimum distance is still the same, d, but the weight is reduced by 1 because we already delete 1 on that coordinate. So the number of xi should be smaller than this one. The length is n minus 1 and weight is w minus 1. The distance, the minimum distance is the same. So we take the sum for n columns, and this is less than equal n times of this one. So combine this one and the previous one, we get m times w smaller than this number, and you get this inequality. And because this is an integer, and actually this we take the floor of this number, but this may not be integer. So this proves the first bow in the junction bow by counting the number of ones. And by counting the number of 0, we get the second upper bow. So this is a kind of induction. Whenever you have an upper bow on the smaller length, you get an upper bow for the larger length. And now let's move to a little complicated case by, instead of counting 1 by 1 submatrix, we're counting 2 by 1 submatrix. So 2 rows and 1 column. And this gives the famous bow called the Plotkin bow. So Plotkin bow say that this apply for code. So in this talk, sometimes I talk about upper bow for code and sometimes constant weight code together. So this is for code. The Plotkin bow state that a and d is smaller than 2 times d over 2d minus n. So now let's play the game again. We write C as a m times n matrix. For easy, we write denote this by CMI, where m is from 1 to m. We have m rows and n column, I from 1 to n. And let's count the number of 1, 0, and 0, 1. So that we count the number of CMI, CLI. So this is 2 different rows, but the same column I. Such that it contains an odd number of 1. So it can be only 0, 1 or 1, 0. So now we count this number by look at the rows. So if we have 2 rows, then we have 2 different rows, and we get the number of such 0, 1, 1, 0 is DUV, which is the distance between U and V. Here is the other pair, U first and then V, and then V and U, so we count 2 times. So the number of such a number S is the sum of the distance UV, where U different from V. And because we have m choice for U and m minus choice for V, because V should be different from U. So this in this sum, the distance between U and V is at least D. So we get this S is greater than this number. And now we count by look at the columns. As before, we let xi be the number of ones on the I column. And now we look at one column. For each I, we pick one from xi and one from one row and the other from m minus xi, because it should be 0, 1 or 1, 0. And we count 2 times. So we take the sum of this. S is the sum of this one. And this is upper bound by a half of m. Let's assume m is even to make it simple. So this is less than or equal to half of m, half of m. So we get this one. So combined with the previous one, we get this inequality. And from here, we got this one. And because we consider m is even, we got the Plotkin bound. But the case art, we substitute this inequality because this should be integer. So si and m minus si is integer. So if we use this inequality, we'll get the same result. Okay, that's it for counting the 2 by 1 submatrix. And a similar version for constant weight codes also, same thing. We just count 2 by 1 submatrix contain an odd number of 1. And the proof is exactly the previous one. We just but here this is a little bit special because each row we have W1. So concentrate on that fact, we'll get this inequality. So I skip the proof. So now this is the very most interesting case is called the number of 2 by k submatrix. K from 1 to n. So when k is 1, this is just will give you the Plotkin bound. But k can be greater than 1. And when counting this one, we didn't expect that we'll get anything, but finally we get the famous Delsarte linear programming bound for binary codes. So now we prove the Delsarte linear programming bound for binary codes. But first, let me define the distance distribution of a code. This is you count the pair UV at distance I, and you divide by the size of the code. And we introduce the polynomial b minus and b plus, which is the positive part and the negative part of the Kirchhoff polynomial. So this is not very new, but it's convenient in our proof. So the sum is the sum of p plus and p minus is nk, but the minus is the Kirchhoff polynomial. So b minus is like for the odd case, the negative part of the Kirchhoff polynomial, and this is the positive part. And this is the key lemma. So we count the number of 2 by k submatrix contain an odd number of 1, and we get the first inequality. This is what we end up with this one. And by counting the number of 2 by k submatrix contain an even number of 1s, we come up with the second inequality. And if you take the sum of these two, you get the Delsarte linear programming bound. So it looks a little bit complicated, but if you try to count, you get the same thing. easily, not very difficult. So this is the Delsarte linear programming bound. Here are the sum from 1 to n, the part 0 I move to the right side. Because in our proof we'll get this one. And not only that, the Delsarte linear programming bound have two improvements. This improvement and this improvement, which was proved later, not by Delsarte. This is the original version of Delsarte linear programming bound is this one. But this one said that this one can be even greater than, you take the sum with some positive integer, it's still greater. And this is similar. The left side is still greater than the right side, even if you take some positive part to the right side. So the later two inequalities are stronger than the original version of Delsarte linear programming bound. But our counting method gives the order of this bound. So the counting method explains what really happened for the improvement. So, and we will see that this is the best we can get from the counting method. So the main thing we do is just counting the 2×k submatrix. So we write C as a CMI as before, and we count S1k be the number of 2×k submatrix. This is on the intersection of two rows and k column, such that this matrix contains an odd number of 1. So now we just focus on the rows and the column. By look at the rows, you will get this number. This is the left side of the Delsarte linear problem. In the left side of in our lemma, and for the right side we just count by look at the columns. And then you combine the two together, you get this one. So, and for the second one, as I say, we can count the 2×k submatrix contain an even number of 1s, or we can use a simpler proof using this equality. This is just the sum of the on AI for I from 1 to n is n minus 1, except the A0. And the new thing happened is, what happened if we do the same thing for constant weight code? So this is totally new. Nobody had done this before, and we tried that one to constant weight code. And here for constant weight codes, we know the information of each row. Each row has W1s. So we better, if we count the 1×k submatrix, we also get some information. So we call this the one row k column formula. By counting the number of 1×k submatrix contain an odd number of 1, you get the one row k column formula. And then we counting the number of 2×k submatrix contain an odd number of 1s. We get the second, the two row k column formulas. So this is corresponding to counting 2×k submatrix contain an odd number of 1s, and the second one is counting the submatrix contain even numbers of 1s. So it's a little more complicated here for the constant weight codes, but the idea is simple. And using this one, We put this one to the linear programming bound, and we get new upper bound for ANDW. We get 22 new upper bound. It doesn't reduce much. It just reduced by 1 by the best known upper bound. For example, this is 4 to 7. It just reduced by 1 from 4 to 8. This is the best known upper bound. And this is our new upper bound. So this is for the minimum distance 6. This is for minimum distance 10 and 12. And we try for the q-ary code, and all of the previous results can be generalized to q-ary code. So here, the definition is similar. Instead of the q equal 2, we allow q is greater than 2. And similar upper bound were obtained. So this is by Swantrom, 1999. They proved the junction type for q-ary code. And this is quite trivial. This is for binary for general codes, and the Plotkin type bound is also proved by Mackenzie and Siberry in 1988, long time ago. And Ostergaard and Swantrom in 2002. So this is this obtained by counting the number of 2 by 1 submatrix. In fact, they didn't prove by that way, but the basic idea is by counting 2 by 1 submatrix. So this is a kind of Plotkin type bound for q-ary version. And recently, we proved the Delsarte linear programming bound for q-ary code, and also its improvement, also by counting method, the 2 by k submatrix. So, the original version of the Delsarte linear programming bound is the right-hand side 0, but it was improved, and the right-hand side can be this number, which is non-negative. So we are not going to give details. So we just give you how we count. So write C as a matrix and count 2 by k submatrix. But now we cannot say odd number of ones or even number of ones, because this is over ZQ. But in fact, we have to count the pair A alpha, where alpha is a vector, and we take the inner product of alpha with the first row and the inner product of alpha with the second rows, and if they are different, then we count such pair. So for the binary case, this is just 1111. So it says that the number of ones of the first row and the number of ones of the second row are different. So that means the total number of ones is odd. So later we realized that the improved version was proved by Ashakmin and Simonet in 1998. But in there, they didn't give any calculation, and we used the improvement to linear programming bound, and we get some new upper bound on the AND over ZQ. This is for Q equal 3, and for Q equal 4. As before, this is only reduced by 1, but sometimes it's reduced by, the only one case it reduced by 2 is this one. It's reduced by 2. And for q equal to 5, all of these are reduced by 1. So you see that here the number of rows is just 1 or 2. We didn't try the number of rows is more than 2. When the number of rows is 1, it corresponds to the weight distribution. When the number of rows is 2, it corresponds to the distance distribution. But when the number of rows is 3, we don't know what's going on there. For example, you count 3 by 1 submatrix satisfies some condition. We don't really know what that will give. So we just stopped at the number of rows is S mod 2. Thank you.
Any questions?